the lecture. In this lecture, we will discover the push-pull converter, which is again a derivation of forward converter. It's a buck converter, and the primary and secondary side of the push-pull converter is exactly the same as forward converter. Just we have another switch instead of a diode. What I mean, let's consider the primary side of the forward converter. Or just zoom in and yeah. This is the primary side of the transformer and connected to switch. Which is again connected to our source. And in forward converter, we had another winding. It was used for reset, and reset winding is necessary for demagnetization of the transformer, the core of the transformer. And we can just simply add these windings with the right polarity, and then we see here a diode, and we said that instead of a diode, we change it with a switch. And this was, for example, Q1, and this is Q2. And the secondary side of the transformer is again a center tapped transformer. Okay. If there's a problem with the connection, just use your microphone or just write me directly. And the secondary side of this transformer has again, or we use secondary 2 and secondary 1. We have again 2 diodes, and these diodes are connected to output inductance, which has the ability of storing energy. What was the difference between flyback converter and forward converter? The difference was between flyback and forward converter. We talked about the differences last week in the lecture, that the energy is stored energy is stored in the air gap for flyback converter, and the polarity of the transformer for flyback converter has opposite dots on the primary and secondary side. But in the forward converter, energy is stored in the output inductance here or here. This was the main difference between two converters. Please, in the exam, be careful by showing the polarity of the um, primary and secondary side of the transformer. So this was for forward converter. And as a load, we usually show our load as a resistance. Maybe it's better to show the grounds of the primary and secondary side different. And instead of a resistive load, we can also use a DC motor or just connect these two guys with each other. And this was our DC motor. Yeah, the derivation of the push-pull converter is based on the forward converter. And there is the second problem in the DC-DC converters, which has transformers, because as you see, there is no RCD snubber. No RCD snubber in such kind of DC-DC converters, and it's the same as push-pull converters. The question was, how can we solve the peak voltages that would be caused during off time of the switches on the drain source? The answer was to look at the secondary side. In push-pull converter, the flux that is built up during the on time will be reflected to the secondary side or will be demagnetized with the help of the secondary side. And for forward converter, these two components were used for demagnetizing of the core. We know that the maximum duty cycle of any DC-DC converter that has transformer should be actually, this was the theoretical value but in the practice, if you remember from the data sheet of the flyback converter that we studied 2 weeks ago, it was approximately 54%. And the question, why can we use more than 50% of the max in the practical applications? I hope you know the answer. We talked about it. What does push and pull mean? That the input current is flowing through Q1 or Q2. It's like pushing the magnetic flux downwards or backwards. For example, this would be pull and upwards would be push. The primary side, the windings, consist of um, two parts, or we can also show our transformer as follows. This is also center tapped, but the input voltage is connected. And on the secondary side, the center is connected to the ground of the secondary side. Any questions up to now? Okay. So we said that the push-pull topology is a derivation of forward converter. That would mean that the transfer function of this converter would be equal to the forward converter. And forward converter is a derivation of buck converter with a turns ratio of the transformer. We have two switches as shown here, Q1 and Q2, and two diodes on the secondary side. We also talked about if you see an inductance in the circuit, there should be always a diode which is connected in series or in parallel. And if you use, in this case, two switches and two diodes, the cost of this DC-DC converter would be probably higher than the forward converter. But the efficiency of the push-pull converter is, again, higher than the forward converter. We have one transformer. These two windings build up the primary side, and they are responsible for the secondary side. And a DC inductor, L of F, actually, this should be filter inductance, and which has the polarity of plus and minus, as shown like that. The important thing is that these two switches are not switched on simultaneously in order to avoid the shoot through of the input source. And there should be a time which is called dead time, that both of the switches are turned off in order to demagnetize, or in order to um, give a time period of for this output inductance to discharge its energy. We will see how it works. And the switching frequency of the primary side is not the same as the secondary side, or the current that flows on the inductance. Here it's written that the output filter operates with 2 times of the switching frequency. That would mean if Q1 has a switching frequency of 100 kilohertz, the current that flows on the output inductance would have a switching frequency of 200 kilohertz. Again, it's an advantage because by this way, you can reduce the switching frequencies, and on the other side, you can reduce the ripple, current ripple on the secondary side. So these are the gate signals of each switches. Uh, be careful that the period of primary side is shown here, which is that the first, the Q1 is switched on, and in the rest of the time for one period, it's always off. On the other hand, Q2 is switched on during this time of period. That would mean we have 3 different modes. Maybe just write it. This is called mode 1, and we will show this period of time as mode 3, and this would be mode 2. Maybe I should for the first mode, which the switching time is defined as like that, this time of period, and let's say this is mode 1. And for mode 3, let's show it here. This would be the time period of from DTS to the half of the period, and or this time of period. We can write both of them. From DTS, from here to here, and or from half of the switching period plus dt less than time smaller than the time period up to ts. And mode 1, then comes mode 3, then we have second mode and again the third mode. And this is the time period of mode 3. And mode 2 is this switching period smaller than plus dt. And this is so-called the second mode. So what happens during mode 1? Mode 1 was that the Q1 is switched on, current flows, or let's show it again with input current, which flows through Q1. And we can define the input and primary side of the voltages. It is when Q1 is on and Q2 is off. The input voltage is seen on the primary side, but let's say on NP1, and what happens on the secondary side? At the same time, the energy is transferred to the secondary side. If we have plus and minus, if we define the plus and minus of the primary windings, that would mean plus belongs to the dot on the primary side, and on the secondary side we have this polarity. That would mean that the flux is built up with the help of the input current, and on the other side of the transform, on the secondary side, the current will flow on D1 as follows. This would be output current, and this would be our capacitor current. What happens on the NS1? We have the polarity here plus, and here is the negative. That means there is no current flow on the second diode. We can define V N is 1 should be equal to, these two voltages are the same, they are equal, and the reflection of the primary side to the secondary side times transfer ratio. Let's define it again with times n. And the current flows on the first switch, but there is no current flow on the second switch, but there is a voltage that is induced also on these primary windings. NP2. That means we have KVL rule can be applied. For example, for this winding, the minus input voltage minus again input voltage would be maybe we can define this voltage also like that. If Q1 is on and Q2 is off, we have a voltage stress on the second switch, Q2, that would mean the selection of Q2 would be 2 times input voltage plus, for example, 20% of um, margin. This was the criterion of selecting the switches for push-pull converter. Any questions about how we found the input and output voltages on the primary and secondary side of the transformer? Okay. So let's look at mode 2. In this case, Q1 is off and Q2 is on. Actually, it's exactly the same as that we had for first mode. And in this case, let's define input current as 1. And in this case, the current, which is defined as E in 2, will flow through this winding like that. And again, input voltage would be equal to minus value of this primary winding, because if we switch off Q1, unfortunately, let's use this guy here. During push phase, the polarity of the windings changes. Um, what does it mean? Or maybe we can make decision like that. The polarity on the inductance doesn't change. Um, if you want to define the input voltage as given like that, uh, mathematically it's correct, but on the oscilloscope of the DC-DC converter, you will see the input voltage as positive on the primary side. If you say that no, the polarity doesn't change, we use the KVL minus input voltage minus the voltage on NP2 is equal to 0, and then we have this formula here. And what happens on the NP1, because we defined here, for example, the input voltage both for NP1 and NP2. They were the same, and here they will be the same. And on the secondary side, again, the direction of the flux changes, and the polarity on the secondary side also changes. V N S1 should be equal to V N S2. We assume that the winding numbers of NS1 is equal to the NS2. They should be symmetrical. We have the same amount of voltages on the secondary side, and again we can use minus input voltage times turns ratio. And the voltage stress on Q1, this is off. That means we should now calculate these two voltages. It's again 2 times of the input voltage. Selection of Q1 is based on the voltage stress and margin. And during the second mode, we would say the polarity also changes. And in this case, here we have plus. That means D1 is blocking and D2 is conducting. We forget the for mode 1, D1 was conducting and D2 was blocking. So maybe we should erase a little bit to show what happens during mode 3. Mode 3 is which the both switches are off. That means the input current is interrupted. There is no flow of input current. But we had magnetizing flux on the primary side, and as we know that the transformers have always magnetizing inductance. That means that the stored energy will be demagnetized inside of the transformer, or should be demagnetized. If it's possible or not, we will see. And what happens here? So both of the switches are off. That means there is no voltage on the primary side. Primary and secondary side of the transformer has now zero voltage. Zero voltage means there is no change of current on the primary side. And on the secondary side is exactly the same. If there is no induced voltage on the primary side, the secondary side of the transformer should have also 0 volts. 0 volts that means this guy here has a potential of 0 volts, and this also has 0 volts. But the output inductance, let's say this point is defined as y of x, and this point is output voltage. And the energy that is stored on this inductance should be discharged. But how? The current should again flow in this way, comes to the center tap of the secondary transformer, and should be equally divided into two, and flows back to the inductance again. That means diode 1 and diode 2, both of them are now conducting. But the value of the current, if you compare with the first and second mode, the current that flows on D1 will be the half of the current of the inductor. So that means during mode 1 and mode 2, we charge up our inductance, output inductance, and during mode 3, the current on the inductance will decrease with the slope of, let's say, this was during, let's say, off, should be equal to the ripple of the current on the inductance. delta T. Delta T is here. You can use this guy or this guy. Just put it here. So we talk about the, of course, for continuous conduction mode. We just forgot to write it again here. Maybe here. This is in continuous conduction mode plus power steady state. And here is the comparison of CCM and DCM operation modes. This is Q1, mode 1, mode 1. Maybe we can zoom in. And this was mode 3. And then this was mode 2. And then again, we have mode 3. As you see here, as the first switch is on here, the voltage across the switch is 0 because the current is flowing. And if you switch off, the voltage jumps to the input voltage. And then if the second switch is turned on, begins to the current flows on the second switch, and we have 2 times of the input voltage as stress between this was drain source, this was also drain source. Of Q1 and Q2. Maybe in the exam, for example, this would be as a question that for the selection of the switches. Any questions? Timothy, Dennis, Paul, Christopher, Namita, and Chen. Okay. So look at the analysis of each modes. I will just okay, maybe here. Yeah. So what happens when the first switch is on and the second is off? There is an input current that flows over magnetizing inductance that we don't see here, but in the real transformers, there's a magnetizing inductance. And on the secondary side here, we have the reflection of the input voltage. That is, we can forget about the primary side. We have now a circuit Maybe it's better to show it like that here, D1, and our inductance here. How do we call? We call this node as okay, V of X, and this was the output voltage. So, and this is our load. As we told before, for the first mode, there is a voltage induced here, and this voltage is equal with this voltage on this winding, the second of the secondary winding, and um, we defined NS1. It was different. Okay, NS1 is on the bottom side of the secondary transformer. Okay, no problem. And now I just want to write the secondary side as follows, like that. This is D2. I use this notation here. Don't be confused. And now we have the current flow like that. And there is no current flow as shown here. So now we have a buck converter. So the secondary side, Vn-S1 is equal to Vn-S2 and is equal to the input voltage times N. So, and we know that, please don't forget to write in the exam this formula here. This is the voltage across the output filter inductance. And how did we define the voltage difference between input and output? It's just the difference between V of X and V out. And V of X is actually equal to this guy here, because we know that these two potentials are the same. So the difference is again N times input voltage minus V out. This is during on time. That means the current on the output inductance is rising. You know, from the previous lectures, we always define dt. This was for on, for mode 1 or mode 2. This is so-called the first mode, and this would be the second mode, and this would be the third mode. We switch between first and third are 1, 3, 2, 3, 1, 3, 2, 3, etc. And input voltage times N minus output voltage divided by, or we can simultaneously carry dt like that. dts, this is this time of period. Any questions before we switch into the second mode or third mode? Okay. So let's look at the third mode. It's a little bit complicated because there is no current that is flowing on the primary side, and the stored energy on the secondary side is we defined here in the third mode that the primary side of the transformer secondary side has 0 volts. Okay, that means V of N is 1, V of N is 2, and they are both 0 volts. If there is no voltage on the secondary side, V of X should also be, let's say, 0 volts. But there is a voltage on the output. The output voltage is bigger than the V of X. VLF was the difference between these two voltages, and this was 0 volts. And the output voltage will be delta T minus V out divided by filter inductance during off time. Yeah. And this current flow here, we also defined it in this formula. This current on the inductance should be output voltage divided by filter inductance times this guy here. Let's say T over 1. the switching over 2 minus dTs, and we can just simplify or simply write it 1 over 2 minus d times ts. And so I will try to write the transfer ratio here. This was off, and we know that the net current change on the inductor should be 0. And what was the, okay, we should use this formula here for on time. Here it was V in minus V out divided by filter inductance times dt plus minus voltage times d times ts. So we can just get rid of the ts. We know that the transfer function of the push-pull converter should be equal to the forward or buck converter times we have turns ratio and just try to solve this equation here. In wait, I wrote it way in times n, yeah. But you don't warn me that I made a mistake here. N times way in, let's say n times way in minus output voltage times D is equal to, this is minus, we can transfer the output voltage on the other side as follows. So let's say minus D times so maybe I can get rid of V out D, and I have here in times N times D, and V out divided by 2. Let's say V out divided by V in should be equal to 2 times N times T. Yeah, the transfer function is exactly the same as the buck converter, but we have a gain of 2. That means this kind of DC-DC converter is much more useful as buck converter. Any questions about how we come up with the result of the formula? Okay. And the second mode was exactly the same as the first mode. Just we use the down, the circuit that is placed on the secondary side, and this was now plus minus n. Let's zoom in. Why don't we zoom in to see that this is defined as n is 2 d2 v of x v out, and so the current flows again like that. Um, During the second mode, that means the second switch is turned on and the flux has now opposite polarity. That would mean input voltage has the minus voltage of the primary side. Um, the secondary side is here. It was minus. This was the voltage on the secondary side of the transformer. This is this portion here. In the practical applications, these times should be, it's in continuous conduction mode. This was minimum value of current on the inductor, and this was the max peak, and this is the peak ripple current, and this time here should be exactly equal to this time here. I would say T1 should equal to the second mode of the operation, T2. This is T1, this is small T2. Break, I'm back. Um, any questions? So we can summarize what we before that. Yeah, okay. Um, the primary and the secondary windings should have the same number of turns. Why? We talked about here for the mode 3 operation of the DC-DC converter. How is it possible that there is no current flow on the primary side here? Maybe we can try to understand it, what happens here. So sorry, my son just came. So during mode 3, this is that time of operation here. That means input current is 0 amps. And we said that there is a magnetizing inductance here and here. There was a switch here, and here they have the same ground. Q1, Q2. And this was the center tapped input voltage. In P2, in P1, second magnetizing inductance, and first magnetizing inductance. So maybe just try to draw the, we know that the I of L is shown like as it is in continuous conduction mode. And this would be minimum input current and the maximum inductor current. Mode 1, mode 3, mode 2. And the input current during mode 1 and mode 3 is 0. We know that there is no current flow during mode 3. And we know that the voltage across magnetizing inductance should be equal to flux dt. dt is the time between what was dt? Between So the question is that here, if there is no voltage during the third mode of operation here, the voltage is zero. And Lm is just a constant. And the change of flux during third mode is equal to zero. That means that the flux should be constant. And we can also show the flux on the core, flux minimum value and the maximum value. During mode 1, the flux increases, and during mode 2, the flux decreases. This is the change of flux, and this is the change of flux. Not up current. That means the flux, net change of flux should be zero. What happens here, according to the formula, there will be no change of flux. No change means the flux should remain constant. And if the flux doesn't change on the primary side, there is no energy transfer to the secondary side. We can maybe note here. Where was it? Oops. Here. During third mode, there is no energy transfer from primary to the secondary, because it acts like there is no transformer in the circuit. If the flux doesn't change, you cannot use it as transformer. Any questions? Paul?
Professor, sorry, can you explain a little bit why there's no energy transfer from primary to secondary? I think I missed that.
Mm-hmm. Okay. Um, you see these two switches here,
Yeah.
and they are both open.
Okay.
Open means we don't have a current flow from the input.
Okay.
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 And but before that, for example, during mode 1, there was a current that was maybe flowing like that or like that. This is mode 1.
Yeah. Yeah.
and this was mode 2. But in between, we have the third mode. That means during mode 1, the current flows on the primary side in P1,
Hmm?
and the voltage on the magnetizing inductance, because of uh, input current, there is a change of input current. Input current rises like that. This was input current. There is a change and there is a voltage across this primary winding. And this is exactly the same on the magnetizing inductance because we store the energy normally in the magnetizing inductance. And suddenly we switch off of Q1. That means there is no current that can flow through this switch or this switch. They are both are open. And what happens now? This is that case. Input current and the input current is now 0 during the third mode. But there was a flux. The flux formula is exactly the same as n times, n means np1 times,
NS1.
um, this is the Faraday law. Faraday law is actually n times the flux divided by dt. We have primary windings are number of primary windings, and flux is also changing with the current. That the waveform of flux is exactly the same as the current here. You see that this guy here is exactly the same as this guy here because the formula tells me exactly the same. But suddenly, in the third operation, the current is 0. There is no current. This is 0. And the flux, if I have, for example, no change of current, the 0 divided by dt, this is 0. There is no change. If there is no change of current in the circuit, and that means that there is no voltage across the first windings of the transformer. The voltage now is here 0. I write now instead of this voltage value, 0 is equal to the first magnetizing, which is a constant number, let's say 100 microhenry times. This should be also 0 in order to have 0, or 0 times a constant should be 0. And this guy here is this guy, because I want to see if my flux changes or not. I would write d phi m1 divided by dt. If there is no change in the flux, it would give me a value of 0. 0 times a constant would be 0. That means the flux reaches this value here and then should stay constant
Okay.
because the energy uh, cannot be transferred to the other side. In this operation mode, transformer doesn't work. It's like a DC transformer.
Like,
You apply a DC voltage at the transformer on the primary side, but you cannot have a voltage on the secondary side because DC, the flux doesn't change. It remains constant until the second mode of operation. What happens in the second mode? Now Q1 is open, and in this case, Q2 is on. Aha, okay. The current now again flows from my source, but in this direction, like that. And if this switch is on, this is off, the polarity on the primary side changes. I assume that this was plus, this was minus at the beginning during Q1 is on. But now the polarity changes. This would be plus and this would be minus. And again, this would be plus and this is minus. The current flows like that. And if the current, due to the current, uh, the polarity changes, if the polarity changes, the flux now should um, decrease because of the change of polarity here. It was, for example, plus, and now it's minus. If it's minus, this is a constant. This has no polarity plus or it's a number. Yeah, it has a real number. It has plus sign, and this should have a minus sign. Minus sign of this guy here. That means it should decrease with the same roll off, I would say. That means this angle here is exactly the same as here due to the equal on times of the switches or off times of the switches. And again, here, this is the third operation mode. It doesn't change because the both of the switches are now off. And then it increases again. What happens if the duty cycles of these switches not equal? I will try to show it like that. It goes again, and here maybe the maximum um, magnetic field intensity has been reached and the core doesn't work anymore. The core is saturated, and we must avoid this point here. We must always control the peak value of the current because the current causes flux and the flux causes that the core is saturated or not. If we can control the peak value, for example, we say, okay, this peak value is reached. Um, the controller that controls the switches, the duty cycle of the switches, should turn off. And we should always monitor these two currents here. They should be equal and they should be limited with a maximum value. And this is a little bit complicated with push-pull converters if you compare it with forward control, converter. Let's look at the secondary side. Um, because on the secondary side here, maybe there is an interesting waveform of the diode. I don't know if you had seen before such kind of current waveforms on these diodes here. Now, if you look at this guy here, this is the current that flows on the inductors. And this is probably, for example, ED1 or 2. Let's say this is the second switch. Switch is off, and here switch is on. And we have, okay, if the second switch is on, the current flows like that. That would mean that this current waveform should belong to second diode. Sorry. I just went through the waveform of the diodes here. So, okay, maybe so. This is I of L. This would be mean and max value, and this is mode 1. Then comes mode 3, and then again mode 2, and then we have the same mode 3. Let's zoom in. I will use exactly this shape here. Current rises and then current decreases and then rises again. And here I have the current waveforms, both of them, both of the diodes on the same axis. So what happens during mode 1? This current waveform is exactly the same as, for example, this current waveform here. it has again a mean value. Let's compare it again here. This is the mean value of the diode. But which diode? Um, Maybe show it again with a different color. So this is exactly the same during mode 1. And I would expect during mode 3 that the current should flow like that. Okay? But I know that during mode 3, during mode 3, the energy on the inductor is discharged and divided exactly into 2. Now, during mode 3, the diode 1 sees exactly the half of the inductor current. This is ID1 and is equal to ID2, and it's exactly the half of the inductor current. Now I will draw the half of the inductor current here. Maybe as you see here in this case, this value actually is exactly the half of the inductor current. This is during mode 3. And during mode 2, in this case, the diode current, this is ID2, and this was ID1. Now we have again the third mode of the operation. I would expect that the inductor current decreases like that, that the current on the second diode has the half of the, I would say this is the value of the half of the uh, inductor current. At max and mean values of the diode current exactly the same as with the inductor current. Any questions? Or maybe we can also illustrate here. For example, if you see, look at this time of interval. So so Any questions? Um, just pay attention during the mode 3 why the current is divided into two. Maybe this is the main important point during mode 3 because there is no voltage that is induced on NS1 and NS2. They are just like shorted, no voltage. So we have another um, technical report of a push-pull converter. Um, this is our input voltage. Input voltage has min and max values. Um, we forgot again. What was the design specifications that we have seen up to this point for the other converters? Maybe just summarize them again. Um, Input voltage switching, yeah, we start usually with switching frequency. Just write here design specs. Select a proper value of switching frequency. Um, Maybe you have also noticed that the period of switching or switching frequency is on the primary side is not exactly as here. That means the switching frequency of secondary side is double of the switching frequency of primary side times 2 is equal to this guy. You see here, for example, this is one period, this is the second period, but here, this is our period for the primary side. We start with switching frequency of Q1 and Q2, and then we define input voltages, input current, let's say E input max here, switching frequency between max and min values. Duty cycle should be less than 0.5. And what else? We have output voltages. We have two output voltages. One is for positive voltages and the other is for negative voltages. Um, Actually, they are both of them are for plus, and they use extra components to have a minus voltage on the output side because we cannot produce if you have a center tapped transform on the secondary side. Um, you cannot use this converter for negative output voltages because the secondary side of any converter that we have seen up to this point, they are always the same. And we will use the same topology. The topology of secondary side will be the same for half bridge and full bridge converters. We just change the primary side, the topology of primary was changed. That means we select switching frequency, and what was the second criteria of selecting the or making a decision of design specs? Ripple current on the inductor between 20 and 40%. The third one, maybe selecting now selection of output inductance and output voltage ripple. And if we decide these parameters, we can easily calculate the losses on each component, and the efficiency can be calculated. And then it was the selection of the drain source voltage of Q1 and Q2. We have extra features in this DC-DC converter, which is under voltage, low output, over voltage output, and the turns ratio. The turns ratio is important if you want to not input to output. Actually, it was, we know the transfer function ratio. If you want to use a DC-DC converter, which has a huge amount of maximum voltage, because let's say we have 18 volts for our gate driver and minus, let's say, 15 volts. We will use these voltages for our gate driver. So the question is, what kind of input voltage should I use to produce 18 plus 18 volts and minus 15 volts? What would be the range of the input voltage? We talked about in the previous lecture that the maximum input voltage shouldn't be far away from the output voltages that we want to produce. Should be around. I shouldn't show it with the equivalent of the formula where in max should be maybe 2 or 3 times of output voltage. Because on the other side, you should use a high value of turns ratio here. If you use a high range of turns ratio, let's say 5 to 10, then the input and output current ratings will be um, the difference between input and output currents will be very high, and the reflection that the reflection of secondary side to the primary um, especially in the previous converters. We had seen that the drain source, maximum drain source voltage on the switches is they are affected from the secondary side. For this reason, the turns ratio should be between 1 and 5 because the maximum value of duty cycle is 0.5, and if you apply it in the formula, 2 times 0.5 times n, that means you define the output voltage with the turns ratio. We have 2 switches here in the controller, LT3999. This is, for example, Q1, or according to our drawings, it was Q2, and this was Q1. We didn't use this SNABA here. It was not um, covered in this lecture. This is so-called RC SNABA. And then we have the rectifier. This is our rectifier circuit on the secondary side, because our input voltage or the secondary voltage um, looks like that. Oops. And the secondary voltage is actually input voltage times turns ratio. You apply a square wave here, and you need a rectifier, and you filter the output voltage, less voltage ripple and less current ripple, and you have here a perfect ADC voltage of output. So we have over voltage protection here. Let's say we have a maximum value of 30 volts here, and this would be, for example, 3 volts. And if you compare the ratio of the resistors here, plus 4. Um, and so I would say we can use 9 kilo ohms here and 1 kilo ohm here. What does this pin do is actually monitor the input voltage, and if it's more than 3 volts, for example, um, the switches are turned off. Or under voltage, we define the minimum voltage as, let's say, 10 volts. 10 volts would mean R1 plus R2 is equal to, let's say, the minimum value in the IC in the controller should be 1 volts, and the ratio of R1 to R2 is again 9 to 1. So we can observe the input voltage, the max and minimum values of the input voltage, because this was the worst case. If you remember, the worst case for the DC-DC converter occurs when the input voltage has the minimum value. The minimum value input voltage would give me a maximum input current. At maximum input current that flows like that or like that, flow through my switches. And the loss of my switches would be high if I use a minimum input voltage. What else can we add to this DC-DC converter? These are for frequency. You can change the frequency of the controller just by changing this. For example, resistance. We should look at the technical report of the controller, and inductor. Yeah, inductor is also defined with this guy here, ripple current, and the, let's say, um, the maximum magnetic flux intensity. For example, if you use a ferrite core, you will have another Bmax, or if you use, for example, iron core, uh, the Bmax would be higher if you use an iron core compared to the ferrite. Yeah, I think that's all. Any questions? The next lecture will be about half bridge and full bridge converters. We have time. I think we can also cover the DC-AC inverters here. So I wish you a very, very happy Merry Christmas.